So I guess we'll start then. Hi, I'm Sutka. So I'll be doing a course on basically using probabilistic programming for scientific discovery. So just quickly going about the structure. So today I'll quickly give the mandatory overview of research at the chair where I'm at TU Munich. Then I'll outline the course content, the breakdown to the 4 lectures, and so what we'll do today and what we'll do tomorrow. Then I'll be discussing in depth 2 big examples of recent work which really pushed the boundaries of what you could do with probabilistic programming, especially if you want to use it for science and mathematics or for physics. But it also generalizes to biology. Then I'll discuss why would we even need probabilistic programming in this context? Why is it such eminent or enticing paradigm for many, especially if you come from, like, let's say, a background where you didn't necessarily take 4 years of stochastics and statistics classes, but you're basically looking at problems in physics or biology or economics, anywhere where you basically have any stochasticity in your model and you want to analyze it in a principled manner. And I'll discuss those reasons in the second section today. Then I'll go through the underlying theoretical ideas. And then I'll summarize the lecture, which should basically be around 90 minutes. By purpose, I've left out inference for now, but that will be a lecture too, just to calm everyone down if you already seen a bit of probabilistic programming and know that basically inference is the centerpiece of everything. Okay, so at the chair, there are basically multiple groups. This one, so Bryce basically does mostly aircraft aerodynamics, mostly focusing on helicopters and basically jets or electrical jets, mostly collaboration with Airbus. Then there's a group which does re-entry aerodynamics, especially at high speeds. If you throw a blunt body down into the atmosphere, how will the boundary layer develop? Then there's automotive, which mostly does work with Audi. Compressible flows, so gas dynamics and cavitation. Mostly did diesel injection in the past, and now they're slowly shifting because diesel is not that hot anymore. Then there's complex fluids. So I mean, with complex fluids, you can basically model anything, going from crowds to just basically changing the viscosity and then moving to different paradigms. Then basically they mostly model SPH these days, which is basically a particle simulation method. Then currently there's the big European Research Council grant, which basically they developed their own flow solver, Alpaca, which is set to be open source quite soon. It's a multi-phase level set solver. So if you want to simulate any bubbles of any kind or any free flows, then have multiple phases, then keep a look out for that. It should appear quite soon. I think they will release it on GitLab. And now what's recently begun is to move to digital manufacturing and free printing, where basically a lot of focus is placed on the phase transition. If you have these small pellets and then you use a laser to melt it, and then you need to model the phase transition. For that, you again use smooth particle hydrodynamics, and that needs to be simulated to make it more efficient and limit the expense of gas, because argon is also quite expensive. So let's go to the course outline. So today, So overall, there will be 4 lectures. So in the first lecture, there's foundational knowledge. Then in the second lecture today, which later today, there will be, I'll discuss inference engines and basically give an in-depth introduction to Turing. Lecture 3 is mostly Bayesian deep learning. There's still a hierarchical Bayesian stuff in there, but I took that out for time constraints and replaced it with basically incorporating GANs and basically explaining how you can incorporate GANs and variational autoencoders in probabilistic programming as generative models. Which so there's a lot of work going towards machine-based design, where you use these oracles, and GANs and VIEs are some of the main tools there. And in 4, I'll give the connection to scientific problems and basically wrap it up. So with more examples and basically also explaining the engineering aspect of how you can, if you want to build such a system, then what tools do you want to use? What do you have to look out for? And how do you have to define your goals to be realistic about them? And well, I think so. The tutorial 1 is already on the GitHub. I'll push the Bayesian stuff, and the GAN VE stuff will be out probably either later today or early tomorrow morning. Yeah, so lecture 1, example applications, why do we need it? And then going through the underlying theoretical ideas, especially conditioning and the different, so like first order and higher order probabilistic programming languages, and how they enhance the general programming language paradigm to basically add the probabilistic paradigm to the probabilistic modeling paradigm. Lecture 2, approaches to inference, then going through around basically give an overview of the current probabilistic programming frameworks landscape with most of the main ones. There's always a lot of flux there because so there exist the big ones which stay in a sense, but there also exist smaller ones which always come and go. So I don't claim to cover all of them. I'm sure I've looked quite a few, but try to cover most of them, which are, as far as I see it, mostly relevant to this endeavor. And then there will be a long introduction to Turing, starting from the modeling layer and then going down deeper into how you can switch auto-differentiation backends, how the auto-differentiation works, and that kind of stuff. In lecture 3 then, Bayesian deep learning is the big one there. And then also basically marrying deep learning frameworks to probabilistic programming and what sometimes is called type 2 machine learning, where some people, no one knows yet what the next frameworks will look like, but there seems to be some move towards incorporating probabilistic programming as a first citizens, which will be quite interesting. So far, you still have to basically cross-program across me and Julia, which I use for the tutorials. You can basically just import the machine learning library, but in the future, they will probably be integrated. But that's still in the future. So lecture 4, I'll then go through introduction with scientific simulators. Something which is quite important there is how you speak to, how you can make a simulator speak to your framework. Especially if you want to use large installations like a cluster or have forbid a supercomputer. What do you need to look out for? And also, what are the hidden pitfalls that you need to look out for, especially there's always this funky business of serialization and deserialization. If you get your simulation data, basically also you just basically generate a ton of data. And you need to really know what to store, where to store, how to access it, how to remember where you stored everything, and also have the system still see what you stored. And then I'll go through a few applications. So machine-based design, I will go through something which is more from the protein design end, which is quite interesting. They have some really interesting work, done some really interesting work recently. Robotics, there's some interesting stuff, and physics. Engineering, there's always quite a bit of movement around generative models for weather simulations and all kinds of other stuff. So let's move then to the examples. So the first one is Etalumis, which is basically, they basically solve an inverse problem. So they use simulate and inverted it. The whole idea is basically that the standard model in physics is really accurate, but so far they haven't really played around with it for inverse problems. So basically they custom built actually this programming system to invert the whole problem and then infer all the latent variables and basically try to map out the latent state, which allows for quite a few insights into model internal correlations, which can be quite useful if you do deal with a black box simulator. But also, if you want to look for interesting traces. So if you recursive programming, you always abstract your simulation as a trace. And a trace is basically, in a most simulation kind of view, it would be the time series of snapshots. So there's also some interesting work on inferring causal graphs from there, but that's I haven't included it here because that's stretches quite a bit. So that was, I think, like 2 weeks ago, where a group from, I think it was from the Netherlands, they basically extract causal graphs from the time series, which one could theoretically do, but I haven't seen anyone do it yet. So that was the first large application of recursive programming to physical simulators. Especially, what's interesting here is the real aim is to really find new physics. They haven't found new physics on the first try because they basically were just looking to really push the scale and show that they can really scale it to a very large machine and make it work efficiently. But they're working on it, and they'll probably try to push it again. It's always dependent on access to the computational capacity, and also CERN always spits out a lot of data when it runs. So they definitely get a lot of data from there. They have a massive scale posterior inference with 25,000 latent variables, which is really high dimensional. So that really governs what kind of inference methods you can use, which I will also discuss in the second lecture. When does which inference method make the most sense, and when you might maybe need to switch, or might need to consider using a hybrid, let's say like doing a few Monte Carlo steps and then using basic variation inference afterwards. And what you can really see at the scale is that the amount of compute required is really dependent on the approach to inference and your simulator, basically, because I don't think I have it on the next few slides, but basically they generated around 150 million samples for their simulator to make it, to basically do this fancy inference, which I will go to in depth in a few slides. But generating 150 million samples, even for, let's say, 2 seconds on 4 cores, is quite a lot of effort. But that's all set to change in the next few years with exascale coming in, and yeah, then if you can get a lot of that machine, then sure, you can do a lot more stuff and do a lot more of that kind of stuff. But then again, the programming paradigm is going to change again. So basically, one of their core contributions was they introduced a new interaction protocol. It's called PPX, the Probabilistic Programming Execution Protocol, which basically allows you to basically link C++, C, and basically everything that's covered by flat buffers. So like Go, JavaScript, but not the traditional HPC languages like Fortran, for example. And this allows you to basically link your simulator through the random number generation. And then basically you can just view it like a normal generative model inside of your probabilistic programming system. I'll explain it more in a bit, and then you can go into there. And basically what they use is this technique called Inference Compilation, which basically uses a large neural network, in this case a 3-dimensional convolutional SDM, to guide the inference procedure, basically amortize computational cost of training. And they have a dynamical compilation process where they can cope with different length of traces. For example, if you lose some data, then your trace might not be as long as the other one. So you can always adjust the length of the data you expect. And then they use importance sampling, which is quite available to inference compilation. But I'll explain inference compilation and the whole concept of amortization, I think, in the next few slides. So the core idea behind all of this is always the shift of paradigm, in a sense. There's that basically you now use simulated probabilistic programs. So as I said before, you view the simulated execution as an execution trace. One whole trace is basically one sample to your probabilistic programming system. You basically sample over the space of execution traces, which is quite high dimensional, but it's possible for some problems. There are always some class of problems where it's just computation intractable. And basically, what one can then do is basically compute likelihoods, automatically learn and construct surrogate models, which is quite of interest right now, which sometimes they're also called digital twins, where there's a lot of movement from this group centered around data-centric engineering. And then you can also introduce other generative approaches into a loop, like basically using a GAN or a VAE for certain subparts, or as an oracle to guide your execution, which basically then allow you to guide the simulation or the inference network in an intelligent fashion, sample more efficiently, and basically get fast inference while still having the same kind of computational expense. So here's a schematic of this. So basically at the bottom you have the simulated execution. This is linked up through PPX to the probabilistic inference engine. So concurrently you simulate, and at the same time you always push back the observed samples. Basically include them in your inference routine, which works quite well, to be honest. Then if you move to the really big, to the inference compilation, then you basically have this core of an LSTM, where you always have the core layers and you have the embedding layers, which you always just attach based on the length of your trace, which then acts as a proposal distribution in your importance sampling. And importance sampling, the better your proposal distribution, the better your inference routine will run, and you win, basically. So that makes a lot of sense. But basically, you always have to consider that you basically still need to amortize costs. So let's quickly, as an interlude, move to amortized inference, because I don't know if everyone here knows that much about it. So basically, the key idea is that you basically try to learn from past inferences to make future inferences run faster. So it's a bit like memorization in a computer science sense there. And was originally motivated by looking at the brain's processing, basically that we always also use context-related information if we look at a new object and we compare it internally to something else that we've seen before. And then constructs this guide program. So in its initial stage, it didn't need to be a neural network. It could be anything. And then the neural network move, as will come in a few slides, was mostly done to basically automate the whole process. And traditionally, most probabilistic programming systems ran on Monte Carlo. Dynamic programming was also interesting for some time, but mostly Monte Carlo is, over the past 10 years, like the most used inference engine at the core of them. So, but they usually have to solve the integral at the core of Bayesian inference from scratch every single time. So basically storing data and reusing it is a really good idea if you have really really expensive simulated executions. In here, basically, it's still a manual construction process, but inference compilation, as I'll show in a few slides, then moves to an automatic compilation process. So here, the original idea was still basically that you look at the probabilistic graph structure of your probabilistic program. And when you then build your guide, in a sense, you want to emulate the graph structure of your original probabilistic program. That's here still the core idea. That has been weakened over time, but in the beginning, that was really a key step, which really made a lot of this possible. And this works quite well. I mean, so initially, you always have the cost of basically throwing a lot of samples at your model to train it. But once you really amortize costs, as I don't know if you can see my mouse, but basically once you have the guide, it's just inference on a network usually. And that's obviously a lot quicker and a lot more efficient than always having to resample the whole shenanigans from your model. Basically let the model run again, and you possibly have to wait, and doing some kinds of inference stuff is a lot more efficient there. So what does inference compilation suggest? So basically they this key idea, okay, we use a neural network to basically construct a surrogate model for a particular generative model, which you can then use at inference time as a proposal distribution to avoid sampling from the actual generative model. Surrogate model is just a replacement model. Main change here is basically the neural network. That you basically have this dynamic construction of the neural network to cope with different lengths of the execution traces. And then you can basically throw that in, and you can just let it run out in automatic fashion. And the automatic fashion is a large part of basic programming, which I'll also show and want to explain a bit more in the more on the theoretical side, and the reasons why basic programming is pushing in research for that kind of stuff. So basically the cost of sampling, so you get amortized inference time, especially if you run it more and more often. You can also obviously apply stuff like transfer learning if you have a similar problem domain, and hence amortize costs even further. They use this adaptive neural network architecture with a recurrent core and embeddings, and there's also an extension by now. If you want to have a look at it, just write in the chat and I can send you the link. So basically they have this extension to transformers now, where they basically put transformers in. But literally they just switch up in the network for transformers. So that's that. And it's completely model agnostic. So they don't make any assumption about the internal dynamics, which is large basic programming. You don't want to have routines which are just made for one model class, but instead you want to try to encapsulate as much as possible to have a general system which you can then use for all kinds of problems. Like basically, if something has out of physics, you would still want to be able to use it for, in robotics is probably too close, but still use it for something like biostatistics or normal data science, for example. But the barrier between those areas is kind of eroding as well. So this is what it schematically looks like. So basically, when you compile, you have a basic program, which you could, as Untitled did, make your simulator, which gives you the training data, which you generate. Then you have put into a neural network architecture. You train it using the difference between distributions, so Library divergence. You have a compilation artifact, and you feed both of those back to the inference routine. And with that, you basically then, once you have the compilation artifact, you can basically run inference on that, and that's the inference compilation, which as said, for these large, latent, basically high-dimensional cases, still requires a lot of samples. So this is what it looks like if you really zoom in on the core. So basically, you have the LSTM core as shown before, and then you have the embeddings, which are just put on adaptively. So that's just to make it as efficient as possible. They also validated for capture generation. So basically, they wrote a generative model for captures and put that in. It works quite well. So to really, going back to Untitled, so they really put a lot of effort into making it supercomputing ready. So they used really pushed PyTorch MPI backend together with Intel. basically used full-on MPI parallelization. I think, yeah, you can see it here. So in terms of scaling, they really, so those are both machines at Lawrence Berkeley National Lab. And they really pushed it to see how far they could go. And basically they couldn't just, the only reason why they couldn't go further, according to some of the guys who were in the group, is basically that they couldn't get more resources. So far it scales really well, but in HPC, you usually hit at that end at some point. So basically the curve that you see here will start to hit a barrier. Communication, usually communication, then just basically flattens off. That's where you hit the wall, and further cores or further nodes wouldn't help. And applying it to particles, tau lepton decay, they were basically able to get these posteriors, which is quite a decent result in a sense. But I mean, the main contribution of the paper is still the computer engineering side. So to sum up what Italum is doing, so what we have here is the first Recursive programming system, which links scientific simulators at scale to enable large-scale posterior inference. But it can only ever capture naturally processes which are encapsulated in a simulator. So simulators in science are always only approximations of the real processes. We can only approximate. We don't really have the true model in a sense. Introduce the Probabilistic program execution protocol, which allows you to link those simulators to the Probabilistic programming system. And then it basically automated the amortization and inference compilation process to basically construct circuits, or in this case, as guides as well. You might also be able to call it an oracle, but I will explain later what especially on the last lecture, I will go more into depth what some people understand as oracle. And it really pushed the frameworks to the extreme with communication, the MPI backend, and all the data which is exchanged between different computing instances and the control servers, basically. So let's move to the second big example. That's quite recent. It's really interesting work, actually. So what they basically did is they constructed this huge Probabilistic programming system, which basically utilizes Bayesian program learning, expanded on an old idea of theirs with wake-sleep learning, where they can basically learn all kinds of programs. So basically they learn meta programming in a sense. And with this wake-sleep procedure, they basically from the bottom up draw a domain-specific language to describe the problem domain. With that, the model then tries to approximate the problem and come up with a solution. If it has to write a program, then that's fine. Or if it has to basically come up with algebra, that's also fine. They also did that. And basically learns, can learn the inference algorithm as well. And in a sense, it's mostly symbolic abstraction there. And then the wake-sleep learning here is key. I'll show in the later slides. So basically during sleep, the system consolidates the abstractions from program found during wake, and it has a neural network recognition model, which then tries to imagine new samples and tries to improve. In wake, the generative model is just exploited and to see how far, then the algorithm basically tries to see how far with its current domain representation it can really push it and really represent the problem. And so basically knowledge, multi-layered hierarchy is quite like a semi-common way to represent your knowledge. And basically you have to bootstrap the knowledge up from very simple concepts in the beginning, like basically just addition, for example, going through multiplication, everything, until you might at some point get up to, let's say, calculus. They didn't get to calculus so far, but they really pushed it with recognizing physical models, as I'll show later. Basically broke down again into this probabilistic inference procedure, which is common again for probabilistic programming, which observes task X and then inferring program rho x to solve the task, combined with the prior distribution over the programs, which might potentially solve the task in the domain. Again, it's this wake sleep abstraction, where basically you have the abstraction, then you have the dreaming, where you sample from this. The neural network recursion model tries to extend DSL partially as well. So the whole thing then basically looks like this. I hope everyone can see this. I'm zoom in. I know I can't zoom in. Okay, so yeah, so during wake, you have this neurally guided search, which proposes programs to fit the problem as good as possible. Basically comes up with its best candidate and it keeps testing iteratively. And then it keeps churning. So basically then it goes into sleep to basically go into the abstraction phase to compress the basically compress the programs down, which it learned in the last iteration, and see what kind of worked. In a sense, in a philosophical sense, maybe it sees what worked well and sees what didn't work well. And then during dreaming, it conjures up new, but the recursion model tries to predict new models, like new programs, which it then later on again gets to try during the wake phase. In between, there's a lot of refactoring, and then as well it has to train this neural network recognition model before it can then move again to the neurally guided search. And the neurally guided search kind of ties in with some work they did, which is basically can be described as like this neurosymbolic concept learner, where they basically are able to kind of also attach concepts to visual inputs, which is interesting work in its own right, but it's not really POSIX programming, so it's not mentioned here. But again, if you're interested in that, just write something in the chat. I'll be happy to send you the paper. So just looking at the full dream coder algorithm. So basically you have the, at every stage, you have your library functions. You have the task that you define. The task changes over time. So that's where you have this bootstrapping of knowledge. And over time, it throws out these libraries, which it keeps adopting, and the recognition model keeps retraining, and the beam is just the search algorithm in there. Yeah, I don't think, so yeah. Just as shown on the graph, basically you have the wake, you have the dream sleep, and you have the wake, and then you always keep some of the, I don't think that was very clear. So made very clear by me so far is that basically you always only keep a few programs which are like the best, and you throw the rest away because they're just a waste of memory. Then again, you have the abstraction phase, and then you always have this updated library, and you process, you update your recognition model as well, and you just keep iterating until you're happy with your conversions, basically. Usually you just look over the epochs, and then if you're not happy, you just throw more epochs at it, which is, I suppose, quite a common view of it. But the problem, the model they constructed is quite involved, actually. So they have a normal neural network recognition model, which is basically written in Torch. And then they have this high performance OCaml backend, which basically has these type modules, enumeration, dream model as well, because into compression. But then again, grammar, program, type, tasks, everything is in Python. Some of it's in OCaml. OCaml mostly for functional fast style of programming. So that kind of shows the challenge that you sometimes have to go through to really attack those problems. And looking at individual models, then you really see that you really have to use the Helmholtz machine here. That's multiprocessing is large, but I think I only really tried it on 64 cores, which for these large machine models is not that large in a sense. But it's a massive mix of languages, which incurs its own penalties, but really goes to show how it basically grows over time, and basically have technical debt. And yeah, it takes a lot of time to construct those models, especially for such a complex problem. So you can really see the earliest work on the direction like 2016. So it basically took them 4 years to really get to a stage where they were able to solve the problem. In the beginning, they were just really solving very simple programs. So just recapping, yeah, I think the header here is wrong. So Helmholtz machine is basically the precursor to, I think I mixed this up here in the slide. So basically, Helmholtz machine is a precursor to a neural-Turing machine. These days, you probably use a neural-Turing machine if you redesign it. I'll speak more about the Helmholtz machine later on, but basically, I'll correct it in the slides and upload it into GitHub again. But yeah, these days, you probably use a neural-Turing machine. So if you would want to use a neural-Turing machine for that, and basically you have attention mechanisms, which basically have read and write heads, and then you write into memory. Yeah, controllers in neural networks. Basically, you have this large memory, and then you basically have selective access to it, and you write selectively to it. Yeah, heavily relies on attention mechanisms, content-based, location-based, and then basically those give you free access mechanisms, content key, content location, location only. Yeah, but that was a bit of a mix-up here. Yeah, those can do kind of the same thing as well, but only for much more simple problems. Like basically they do sorting algorithms. But usually you would put those into the core of your programming system these days. So if you want to redesign it, you probably use a neural-Turing machine these days, or even a differentiable neural computer, because that's even better, because it really is, it's made for operations on graphs, which really suits programming systems well, because they essentially basically compiling down into graph representations. So that really works well in there. So let's have a look at some of Dream Coder's learned applications. So basically, this is basically a list sort, which was also done by a neural-Turing machine, but so they construct this library of concepts, and over time they basically are able to learn the best algorithm for that. And basically they represent it in some basically a Lisp dialect there. But it's still bootstrapping of knowledge, so that's something you always have to consider. Basically, neural-Turing machine is one shot. And just overlooking a lot of the other applications that it is, list processing is kind of direction of sorts. Basically, how you stable towers, recursive programming, no graphics, symbolic regression, which is quite a large thing currently, and also they were able to learn some physical laws, which is again bootstrapped from very simple applications first, and then moving to the more difficult ones, but not really scaling it in this work, if that makes sense. So here looking at the physical equations, for example, and you first start with these very simple vectors. Then you basically have the operations, how you combine those vectors, and then it begins to really think of constructing those physical laws. And those are just the, there's also kind of compared to this paper by Max Tegmark, where they also learn physical laws, but they basically just used the physical equations defined in Feynman. That's kind of in the same spirit here. Very different approach, but kind of. Then recursive programming as well, it's like basically they first learn the very simple programming operators and then combine them successively to get more and more towards these more advanced concepts, and then being able to address those. This is for basically how you can generate graphics, which is also quite interesting in its own right. Yeah, I don't think there's much to say to it, to be honest. This is for list processing. Again, bootstrapping. Usually you store everything in Lisp, so you can still kind of manipulate the expressions because Lisp has metaprogrammability. Yeah, so the main takeaways here. So basically combine probabilistic programming with these DSL or domain-specific language learning procedures and non-probabilistic inference procedures like wake-sleep. To achieve learn to represent domain's problem is a really interesting approach, which has a lot of promise. But they require highly complex code bases. And in this case, or across the cases actually, spanning multiple languages. And for more complex cases, you really run into this problem to make inference tractable, which again moves into something which is at the core of basically all of basic programming, that your inference needs to be tractable, and someone needs to make it tractable, whatever it takes. And probabilistic programming systems, they usually use automated systems for that. So let's move to why do we even need probabilistic programming? So basically, the myth probabilistic programming, which everyone seems to be kind of striving for, but what's far way off in a sense, is this idea of automated inference. Hey, I just give you my models, and basically the probabilistic system runs with it and gives me the model statistics back. But not solved, especially because there exist so many different kinds of models, so it would be really hard, or it is really hard, to have one inference algorithm to cover all of those model classes. And then again, you have these problems of high dimensional and that given architecture innovations, which took away a lot of the constraints of past probabilistic programming frameworks, probabilistic models have gotten a lot more difficult. So encapsulating those in one unifying inference algorithm is obviously very, very hard. Then side effect in the sense of that is that basically, if you say you're a data scientist and you really just want to do some Bayesian statistics or run some statistical analysis on your data sets, you don't really want to have to code the inference routines from scratch. That's a highly fraught process. It takes you a lot of time, taking away from your actual intent, but also at the same time, your routine will probably never be optimal because you haven't studied the problem. I mean, it's not your purpose, right? So you want to do the statistical analysis, but for that you have to have the inference algorithms, and those are exposed to the user, or made more so available to the user through its probabilistic programming frameworks in a sense. You can find these isolated algorithms as well, but having that in a coherent platform, which allows you to condition on observations and run statistical analysis in a principled manner on your data set, has a lot of advantages. On the one side, it makes it a lot easier for you, and you can focus on science or your analysis that you're doing, but also it makes your results a lot more reproducible. Then very much to the core of all of this is you want to accelerate the probabilistic modeling research cycle, which basically describes that you first pose your domain model, then you use the inference algorithm, then you refine the model and repeat the whole process again. And in the past, you would need to rewrite the inference algorithm every single time. But with these model algorithms, you don't need to do this anymore. So that's a massive advantage then. Another thing here is obviously at the core of Bayesian statistics in a sense is you really can natively express uncertainties over your models. That's especially if you have to make critical recommendations or decisions, being able to say how certain or how confident you are in your prediction is really useful. And that's really all of probabilistic programming is built around Bayesian statistics. So that's there. And that's also why it's really useful for a lot of people. Then in a sense, kind of comparable to what you can kind of see in deep learning right now, where in the past, at these very early stages, you were quite constrained in terms of which architectures you could think of. And with modern systems, you can think of much more difficult architectures. And it's the same thing here. So basically, there was a huge influx of new ideas, how you can construct these probabilistic programming frameworks more flexibly, with the central core of the inference and the modeling part built around it. And that then basically culminated in basically people expressing the models or thinking of more complex models to try to represent their processes. And also, you want to express your model in as few lines of code as possible because it's the fastest way. So if you can express your processing model in, let's say, 10 lines of code, that's great. Sometimes it might not be 10, but a lot of the distributions and the boilerplate code behind it is kind of abstracted away. So you can express it a lot more efficiently without having to go if you're being able to argue, let's say, on a high abstraction level, which makes the normal user more efficient. And then as well, you want to the whole enterprise basically lowers the barrier of entry to Bayesian analysis. It's readily available now. You don't need any expensive software for it. And documentation is usually quite good. So let's move to the underlying theoretical ideas. Yeah, I think I'm out of time. So actually, I think I might be ahead of time actually. So let's look at it from a research perspective. So what are research ideas that I and other people are interested in? Basically design languages which are able to express our problems or basically provide more expressive semantics, have interpreters running in between, compilers, which is in a sense a byproduct where you basically translate the inference problem into the mathematical objects, especially if you want to relate it all the way back down to measure theory. And then you want to have what's really at the core of it is this integration of modern inference frameworks. And then there's still this push of developing new inference routines, of course, especially for model classes, which are not really well captured by current inference algorithms, especially if you are like on the high end of, let's say, very expensive models, then usually the inference routines one uses there are quite different to a normal longitudinal dynamics or something like that. So let's start with the model-based reasoning, which is at the which is one of the core concepts here. So you have these random variables and probabilistic calculations are core requirements. So again, it's basically probabilistic machine learning there. As said before, all our models are just approximations of reality. We have to be aware of that. And our numerical models always emulate stochasticity through random number draws. And with that, we get our stochasticity in there, and that makes it really amenable then to probabilistic programming. But again, it's also responsible for random phenomena and introduces these uncertainties. And especially if you have all these different states that you could just have at one decision, if you just span up the decision tree, you can have a massive tree very, very quickly. So you have this massive space, which you want to get some insight in, basically. And that basically is this explosion of possible states and division nodes on the graphs of your network. Then, of course, a good model should be able to represent all possible states of the real world, but that's more of an ulterior motive, which you're not really always able to accomplish. But we all have to be realistic about that. So to really explore the space of the models, you need a really large population of model executions. As said before, you need a lot of samples to reach statistical significance. And basically, the model allows you to measure the value and phenomena which take place in the real world, and you can observe them into your model. You want to relate those to. But again, we are not able to capture every detail of the model, be it for physical reasons or numerical constraints. In a sense, also computational complexity plays into that. And of course, if you want to use it in science, the easiest way to use it there is basically Bayesian negation. So if you do a statistical validation of theories, if you construct a model of that theory, statistical model, then do inference on that, and you don't end up with the kind of results you expect, and then either you implemented the model in the wrong way, which is always the first thing to look at, but if not, then there's probably something wrong with the theory. So then that you can kind of expose weaknesses in the theoretical understanding, especially if you have to combine with something, let's say adversarial sampling, for example. And also statistical decision-making and uncertainty is also directly possible, especially because uncertainty is already included, and so you're able to present it in a model, and so you're able to argue based on the model. So what does usefulness of your model mean in this context? So there exist multiple kinds. You can either have a usable model, which also provides an interpretable abstraction, but doesn't necessarily need to be interpretable as long as it gives good data, basically. You might not be able to interpret your model, which might be an issue if you're in something like if you're working, say, inside of a power plant, because there's a lot of security attached to it, so you need to know what's happening inside of your models. But if it's basic physics, then you might be able to go around it. And then again, the last kind is these problem-specific simulators, engineering, natural sciences, biology. I think mathematical technology is also good for that. They're highly accurate, but they might be really expensive. And then you again run into this paradigm of needing to amortize and inference compile. All models are parameterized, though, so we can always do model fitting, which is quite good. So how are models denoted and how we can manipulate them? So we always condition on our sets of observations to arrive at the main joint distribution. For this, we always have to consider base rule. Then our model is then at the end is the joint distribution P of yx. The observation is y, and the random, there's a typo, random choice is made in generative model x, which we know as the latent variables. And the setup then, this very general setup is able to encapsulate a lot of the problems that we face or that we deal with in science, or in general, if you do statistical modeling, then a lot of those problems can be made to fit into that mold, basically. So basically looking at what are examples. Recursive programming is able to scale and do inference on something, or do inference on a pair of variables, which you wouldn't really be able to do if you do a manual scaling, for example. And then here, for example, if you have basically from images generating a scene description, is something which really can be quite difficult because you're arguing on an image level, but recursive programming can do that. As I'll show on the last day, there exists some applications or some examples in robotics where people really, they have an agent, and just by the image domain, he's able to navigate the domain and really understand and basically inference on the fastest path from point A to point B with barriers in between. With simulations, it's always just the simulator output. That's quite classical. But you can also do basically just whole program code, which basically gives you a program return value. Then again, policy priors and reward simulations, which can basically give you rewards. So then you're kind of in a model-based reinforcement learning paradigm, which you can also make basically fit the whole thing into, which you can kind of integrate. So that's kind of in the spirit of what some people call reactive recursive programming, which is made to really adapt to domain controls, for example, in industrial environments. There's a really good paper on that out from Michael Carvin. Then also there's this whole area where some people like Noah Goodman are very famous for. It's like cognitive decision making, where they motivate everything from the cognitive side. And Joshua Tenenbaum is also coming from that angle and basically try to observe behavior and then use these models to explain that. So the first with images is kind of comparable to the capture example, which was used for inference compilation and amortized inference before. everything that you basically need in that context then is you need a good probabilistic program, which sounds simple at first, but once you have to write the probabilistic program down for a complex case, it might not be as straightforward anymore. Yeah. Again, here, approximate inference to make inference tractable. Then you have to really use the sample from posterior to get the right results in a sense. And you always want to condition on the existing values, which is always key. So conditioning is one of the main concepts here, or in general for the program, that you always condition on observation that you already have. And yeah, in here, you're not, so I don't know how many of you took the course, but I think the Introduction to Bayesian Statistics course, I think it was last week. And I think you use STAN, which is more of a statistical blend. But as you will see later today, that's really, modern frameworks are quite different. They're not really constrained to just statistics anymore. And so these modern frameworks, one of which we're also using in this course, is they really don't constrain you to just statistics. They want you to play around and basically insert neural layers, insert attention layers, memory layers, and if you can express it on paper, basically in mathematical formalism, then you should also be able to implement it in the framework. That's a rule. For example, STAN doesn't have any linkage to, let's say, a deep learning component like PyTorch, TensorFlow, Flux, and to a lesser component. So it's looking at the definition here. So basically, normally in computer science, you'd use the parameters, or engineering as well. You have the parameters, you have the program, and then you generate the output. Then in statistics, you have your output, and then you try to move in the opposite direction, infer the prior. And in here, it's kind of like can be compared to a Bayesian model inversion in a sense. You kind of have your observations that you know, and using your forward model and repeated simulations, you want to infer the parameters, where it comes from or where it could come from. And that basically, as it's not discrete, you would have a probability distribution there. And one of the big examples is also, you can basically have this for constraint simulation. So basically you define constraints. You could also have this for coming more from my angle. You could have it with a flow and basically saying, I'm constrained to this in this domain. With flows, you obviously also have to consider boundary conditions, but you could kind of try to push that into the statistical area as long as the interactions from the boundaries don't push back into your main observation domain. Then again, if you, let's say you generate body poses, which is one of the recent applications, or you try to generate 3D objects, then having constraints is quite natural, and probabilistic programming is very easily able to do so. So let's start on the more, like, going a bit more to more theoretical side. So first we'll construct this, go over this first order probabilistic programming language, which basically introduces the core concepts on a reduced set of language concepts attached to it. And then that expands out to a higher order, which is then again moving more towards these modern languages, which are nearly all higher order. And some of them are even Turing complete these days. So yeah, let's say first order probabilistic programming language, no functions as arguments giving to a function, so you no recursivity, and only a finite number of random variables in the model. Those are the core outlines. And basically it acts like a very good graph compiler. Any program that you can express in this first order probabilistic programming language can be compiled down into a graphical model, and is then highly suited for graphical model data structures. There exist quite a few examples of that. So the first probabilistic programming language has 6 core rules, which are non-statistical, and then there are 2 rules which are coming more from probabilistic programming side. So I can just quickly go through them. Constant C can be any type of, can be a value of a primitive data type. I think it's fairly straightforward. Variable is a symbol. That's I think it's also a format. Straightforward. Let binding variables to expressions. It's fine. If else constructs, that's pretty normal, I think, for all of us. Then function application calls unit-defined function. That's also, I think, pretty normal. Built-in function C here can also be a plus, a minus, a multiplier. That can be something really basic, or it could also be something a little more advanced, but in a sense, usually assume it to be something quite basic. Then the probabilistic probing specific features are then that you have to provide a sample statement. You can sample from a distribution, and the observe statement, which basically, So the observe statement just returns the next argument, whereas the other one returns a value. So that's, I think, so in the research, basically where you have this general programming language, which is then extended with these probabilistic programming features. Those two main components are, if you want to have a first probabilistic programming language, which is like a simple thing you could probably construct on your own in a day or so. Those two concepts are the one that you need to implement, basically. Then again, if you want to express our inference or our model in the first probabilistic programming language, then we need to build on those concepts. We can combine them, but we cannot validate, for example, the functions, accepting functions argument utility, or we need to really watch out that random variables are always a finite amount. So looking at an example code here, that's more of a Lisp dialect for hidden Markov model. You have the sampling, then you have the observes, and then you append the states, and generate data from discrete distributions with the likes being normally distributed. And you put them all together into you have 16 states basically in the hidden Markov model. I think a lot of the foundation work had been done, or some is still done in Lisp. So the Lisp syntax is your frenemy. But yeah. So let's move to more of a higher order concept here. So what does the higher order programming language, entail? Obviously, higher order procedures, general recursion. You can theoretically denote models of an unbounded number of random variables, but that's again then intractable for inference. You really need to watch out. But again, because it's so large and has more abstraction layers to it, more depth in terms of concepts, you cannot really apply graph-based inference strategies, which you could still apply on the to the first order probabilistic programming language. So the main tool here then is evaluation-based inference, where you constrain yourself to find a number of random variables at any one time. Then function recursion, that's all good. Stochastic recursion then becomes a bit more advanced, but it's quite interesting because you can construct a lot more complex controls with that. And then with that, you can theoretically very easily implement an infinite number of random variables. But yeah, you need to watch out for that because obviously your system will crash basically. And then this is kind of an example. We basically have the stochastic recursion. You have this nested sampling and a geometric helper, and basically just end up with an infinite number of random variables. You can control it, and it becomes it's intractable to sample at some stage. So yeah, this so far has not been related to. Showed in Lisp code, but basically the main concept is not constrained to any language. So you can embed higher order probabilistic programming language in any programming language if you want to. You need to provide basically provide a library which extends some of the routines, but that's fine. Yeah, I mean functions locally, and there's all these languages which have that church. He says seems to be more viewed as a background paper, which basically established a basic system on which Venture and Anglican then built their systems, and I'll go into Anglican, explain what Venture did and what Venture did good, and yeah, there's I think the systems from like 2014, 2015, so these systems aren't used today anymore. WebPPL still used, Pro6C, Turing. Yeah, that's the one we'll be using for the tutorial later. CP-prop, I must confess to have not worked with it. That comes mostly down to, as I'll also explain later, the kind of features that you want for your models and the problems. And C++ was just not the right language for my problems. Basically, if you enrich your higher order probabilistic programming languages with some specific features, then you will turn into a superset of a first order probabilistic programming language, which I think is quite intuitive in a sense. But also which is new compared to a first order, is that you're able to define these open universe models, which can basically adopt like the loop depth, for example, or the loop size as well. That's really interesting because that gives you tools that you're, say, quite used to normally from, let's say, something like a Python, if you use the loops in there, for example, or other normal languages. But yeah, for that, you again need to constrain your sampling algorithms to make it tractable. Yeah. Using Lisp dialect, you're always able to construct these mathematical expressions. It's quite a common try to do. Dreamcode obviously takes a bit further than just the simple expressions, but this was the start basically. Especially if it's in Lisp or in Julia, you can let the whole system, like a higher order probabilistic programming language, write its own code as well. It's quite expensive, of course, but it can theoretically program itself with the right inputs. But then again, it turns into sampling on a space of functions. The number of combinators that you define to a function then controls the size of the space of all functions. So if you have 4 combinators which define your model class, then that gives you dimensionality of your latent space in that regard. And then you invoke the generated function with the eval. And but then again, just a disclaimer, this concept of a higher order probabilistic programming language in itself is still, it's kind of limited, so it still needs to be extended, but it can be extended in terms of its own features and building up these features for run, interrupt, resume, and fork, which are basically the features that you need to implement inference algorithms on top of it. So just going through a few more advanced ideas now. So basically, this is again moving to a direction of meta learning, basically, where you try to learn the model itself. And this is mostly motivated by, we can hear from people like Rich Sutton, for example, basically say, it doesn't make sense to encode problem-specific features, but because large data will always win on the scale of data. So using a data-driven approach basically should always trump hand-design algorithms in the long run. But again, it's dependent on a lot of hand-labeled data. So yeah. So in here, you try to learn the general model itself. but again, you have to follow this bottom-up approach. The bottom-down would be where you program at this high level and then compiles down, but bottom-up is where you start from the variables, the latent variables, and basically try to construct everything from the bottom up. This sometimes works, but again, this is if you have a more difficult problem, then your problem again becomes intractable. Yeah. Then again, this combination of intelligent agents, kind of in a sense like inference compilation or amortized inference. But then again, this in here it's mostly raised back to cognitive science, where they say, okay, what they really like to do is construct the world model. So they let the model, when it tries to construct a new model, construct it from its own world model. And for that, they traditionally have used the Helmholtz machine. Extension of that is version autoencoder and neural Turing machine, differential neural computers. So this is what the graph for a Helmholtz machine would look like. So basically you have a hierarchical model where the encoder basically learns this representation model, how it writes onto the latent states. The decoder then writes it out. With that, they can very generally relate these different domains. But then again, here's the hidden caveat. So some say, especially program synthesis, which has this aim of merging, let's say, two POSIX programs, that you still want to impose structure. Yeah, that's from a program induction direction. Sometimes it's easy to impose prior structure, but sometimes it can also be quite difficult. So that's something that you have to keep in mind. But so far, there's no proof of concept paper yet where they can really show that you longer really outperform the top-down approach, where you write your programs in a high abstraction level, impose the programming system, and replace it with these models. The other thing that's still really interesting here is nesting. So nesting programs is extension of current ideas, basically you treat a high-order recursive program as distribution and then use it again in a different program. So you basically use a program inside of a program. And in terms of computer science itself, it's mostly about, is it really defined? And can you really define this? You can really define this object mathematically. And the answer here is that, interestingly, sometimes you can't really, because it's non-unique in its description there. And at the same time, it's doubly intractable if you choose the wrong problem. And there's quite a bit of work by people like Tom Rainford from Oxford, where basically they show that these, if you use a doubled Monte Carlo algorithm, for example, then most often you will rather preserve the traits or the bad traits of the inference algorithm that you're initially trying to get rid of, instead of really sharing the good traits. So that's an issue that you have to cope with. And there are strategies to combat that, but it's quite touchy. And again, you move into this domain where you hand construct inference routines for a reduced class of problems, which you try to avoid. So in a sense, maybe something like a Gibbs sampler, which would be combined with, let's say, Hamiltonian Monte Carlo and a particle sampler, would then be a lot more suited here. Again, in here, especially with nesting, so far there's no clear language construct or clear understanding of how you would include it in your normal language construct. So that's one of the main problems there. And inference, as I said, is very touchy. The measure theory or the support of your distributions can't really be defined between the two distributions. There's you don't really have the tools for that yet. But if it would work, hypothetically, people are really interested in basically using it for like multi-agent stuff. So multi-agent reinforcement learning is quite big, but then if you'd have these multiple agents which could really interact and also have their internal world models interact and influence themselves. It would be quite interesting for using them for like social studies and things like that. All right, I think I'm running ahead of time actually. So I think in terms of the course, I'll basically wrap up the summary here, and then I'll quickly cover the first few inference algorithms of lecture 2, basically the Monte Carlo algorithms. And then we will start the lecture in the afternoon with the variational inference algorithms, and then we can spend a lot more time on the probabilistic programming systems and the introduction to Turing. So just to summarize, this the first lecture basically. So in a sense, programming enables new, also thought-provoking applications, which allow new combinations which you couldn't really see before. At the same time, they require interaction between inference routines and machine learning building blocks. And we'll do a lot of this in lecture 3. We'll be combining a lot of probabilistic programming with GANs and VAEs, and also Bayesian neural networks, and also for Bayesian differential equations. Then the concept of conditioning enables many applications across science. You'll really see that in the notebook if you maybe have already opened it. Also, inference routines will be later today. For Monte Carlo, probably do it right now because we still have like 10 minutes. Auto science applications, that's happening tomorrow. And the main constraint here, as we could see from these first order and higher order programming languages, that we really need the right modeling syntax to express our class of problems. And that's where, as you will see later today, a lot of the shifting happens between programs which are built for, let's say, a certain subclass of problems, and then probabilistic programming systems which are built more so for these larger scale of problems. So let me just quickly pull up lecture 2, and then I can start there as well. Okay, how can we switch? Ah, there we are. Looks good to me. That worked well. Okay, sorry, I'll probably have to, let's do it like this then. Okay, so now we're already off to lecture 2. Okay, so this is how lecture 2 breaks down. First, the inference engines, which are the core of probabilistic programming systems. First, the traditional Monte Carlo style, then variational inference, which has come more into fashion in recent years. I'll hope to explain why. Then I'll go over some of the larger probabilistic programming systems of the recent years, basically. Still including stand for historic reference, but yeah, I mean, if you, yeah, for the purpose of this course, that would make a lot of sense. And then in the end, we'll have this larger introduction to Turing. So let's start. So basically, this is what the layout of a normal probabilistic programming system looks like. So you have you have a domain-specific language usually defined by your probabilistic programming system, in which you have to define your probabilistic model. Sometimes it can also be just normal Python code in a sense, or normal Julia code, which is enhanced with probabilistic capabilities, which is quite nice, especially if you come from because you can get started really quickly. But again, DSLs have their advantages, especially if you work in if you need something like automatic differentiation, then it becomes a bit harder to get those tools if you just use a normal language, for example. And that's why they initially implemented all those DSLs. And then, yeah, the inference algorithms, then you have a usually black box sampler, and that gives you results. Yeah, I mean, the more expressive the DSL is, the more models you can express. But most DSLs do usually have some kind of constraints in what they can represent. So when looking at a new problem and looking at the available tools for the problem, then it's always a consideration first looking at the way the DSL is defined in most often actually a source code, and seeing if the modeling constructs are the ones that you need to really define your model. Then you provide a library of inference algorithms, which is the core of Recursive programming, that really needs to work well. If it doesn't work well, then yeah, why would you want to use that platform? And the prevalent for the past few years has been Monte Carlo, but variation inference approaches have their own set of strengths, especially high dimensions and computational compute constraint, basically, where let's say you have much less compute than you would ideally like to. Monte Carlo always gets to the right posterior, but it takes a lot of time. So you would then either do a hybrid strategy where you basically do a few Monte Carlo samples, get a better initialization, then do variation inference. Or you do something like just set up variation inference where you say, okay, hey, I sacrifice some accuracy and basically transform it into an optimization problem where I try to use a parametric family to approximate my posterior as closely as possible, given the computational compute I have. And this combination is really important because when using it, you really need to be aware of the inference algorithms that you use, at least those, and the strengths and weaknesses. So if you define your model, if you use the wrong model or the wrong problem on the wrong inference algorithm, then they might return funky results, and there's no real protection from that. So they exist work where basically some people use Haskell, for example, to define the probabilistic inference routines. And if you are able to define your inference routine and your probabilistic model in that it's a proof of concept. So basically, if you in a very constrained DSL and it compiles, then it will run. But it needs to compile. So that's one way to test, I suppose. So let's look at the very traditional ones at first. So the most traditional one at first is when people say things. Some view it as stochastic model finding. It's the most simple Markov Monte Carlo algorithm in a sense. Still used as a building block, especially in sampling, but you wouldn't really necessarily need to sample these days from your actual model, and probably rather use something like a surrogate, because if you use something like a GP surrogate and sample from that, then you save yourself the actual evaluations of the true model, which is usually a lot more expensive. So again, you're moving to some kind of analogy to the amortization paradigm there. So this is the original algorithm from which then Langevin and particle methods evolved. And breaking down, basically for every sample that you generate, you calculate an acceptance ratio. Because it's running what things, Q of xy and Q of y given x are the same. So they just eliminate each other, and basically you end up with a very simple acceptance ratio, which is then integrated into Markov Monte Carlo or Gibbs sampler. And usually you have, so basically you have your acceptance probability, and then you do a sample from uniform distribution, and if it's inside, then you keep it, and if not, you will just stay at the current point, and then do again a multiple processing step and see where you might want to move to. So Hamiltonian Monte Carlo is a massive development on top of that, which really evolved the field, and over the past 10 years has really found its own stride. So random metropolis Hastings basically at the edge of its exploration zone, the acceptance probability vanishes. And the approach that Hamilton Monte Carlo takes is they basically transform information geometry to sample more efficiently on this transformed space and then project back into the space where you want to do the exploration steps. So basically you endow the space of a Hamiltonian structure, which is kind of like infusing velocity here. You basically channel it through the momentum part of the Hamiltonian. Yeah, you follow the Hamiltonian vector field to generate trajectories, which can then be projected back to a type parameter space to generate efficient exploration trajectories. Algorithm is basically, so you project onto the phase space of the Hamiltonian, integrate Hamilton's equations to get projected exploration trajectories, and then project those back to your additional target parameter space. So this is how you define mathematically. So you have an exponential distribution with the Hamiltonian and exponential. Then you decompose it into the momentum and position parts, which again, the relation between those two has to abide by Hamilton's equations. From this, we can get the posterior distribution out of the potential energy function with especially the prior and the likelihood function there. So this is a slightly older sketch of the algorithm from Neil Rutherford. So usually use something like a leapfrog integrator to do the steps on there these days, but in here you still have the normal half step. Then you basically loop over those steps, do a half step for momentum, then you evaluate, and then you have again exceptions rejection step, which kind of builds naturally on top of the ideas, excluding the type parameter space transformation. It kind of builds on the ideas of metropolis Hastings in some sense. So if in an idealized case, that's what it would kind of look like, that you have kind of like a cone structure nearly, or like a bowl structure, and you would mostly move around here in the lower part, and hence really avoid those high regions where you don't really want to sample, and hence save computational cost, which makes perfect sense and performs really well. So comparing to random walk metropolis Hastings, you see that you cover the space a lot better with your samples. And the standard deviation from the coordinates that you try to find is also a lot smaller. So it's superior in all aspects. But of course, for some time it had been a lot more difficult to implement these transformations automatically, but that has been solved by now. So by now you wouldn't really need to you wouldn't need to hand specify the transformation, but Stan, for example, or Edwards or Turing, or I think like most probabilistic programming systems can do the trick for you. And I think that's where we'll stop for now for the morning lecture, and then we'll start with stochastic gradient longitudinal dynamics in the afternoon, and then move through stochastic gradient longitudinal dynamics, version inference, probabilistic programming systems, and then move to the looking at Turing in depth. So thank you for your attention. I'm not entirely sure what I'm supposed to do now. Oh. Okay. Roman. A good question. So yes, we can start the lecture early. The problem with crowd computing is that if you do like what we call leadership class applications, then a lot of the performance boils down to the interconnect between different modeling instances. Like we move a lot of data from RAM to disk, from RAM to the processor to keep the floating point units fed. And you have to move it in between, which is why you have, for example, a 200 gigabit Ethernet or infinite band network on a supercomputer. So for something like folding at home, you need something which is like model-based parallelism with very little communication. So if you can fit a problem into that mold and make it act in a model-based parallelism sense, then yeah, sure, it works. But you also have to consider that a lot of the stuff that you run on these large machines and scientific computing clusters is often like mostly proprietary code. So you wouldn't really want to move it to, let's say, a third person's machine and run it on there. I guess you can solve it with containers, but I'm not too sure. Biostatistics, yes. I will talk a bit about that in the fourth lecture with the basically machine-based design, which they basically use to design proteins these days. So there's this very interesting work between a group of Francis Arnold and one of the New York professors at UC Berkeley. I'm afraid I forgot her name. Linguistic programming. Interesting question. So there exist these treatises like Introduction to Basic Programming, but it's things like 2 years old now, so you can make an argument for it being slightly outdated. I guess reading papers from PropRock, like the Basic Programming Conference, which I think this year is taking place online in September or something like that, helps. What also usually works quite well is just, given that you already have some programming background, you can probably just try to comb through some of the basic programming codes. That's also usually a good starting point. I hope that kind of answers your question. I'm not too sure what, I don't think there exists like a set list of papers, for example, which you would do to get to that point. But please message me if you want a more specific answer, or if I can maybe give a better answer in some other way. Any more questions? Yeah, I think so, yeah, Okay. I think that's for the morning lecture. I mean, if you guys want to do the second lecture earlier, that's I guess it's fine by me. Just vote, I guess, and then we'll see. Right, so I guess we are back. Let me just switch to lecture 2. So I'll try to keep track of the Slido, especially in the comparison of recursive programming frameworks. So if you have any question there, please just write into the slide and I'll try to address them as soon as possible. So we can just move that out of the way. Okay, okay. Let's get cracking. Better. Way better. Okay, so that's I think where we stopped. Yeah. So then so one of the core ideas that came up in like the past 10 years basically is also this idea of stochastic approximation for inference algorithms. So as you will see in the on the Bayesian inference stuff, that has permeated the whole field of Bayesian inference, especially in the context of recursive programming in recent years and scaling it up to much larger levels, much larger problems as well. So the core idea here is this stochastic approximation algorithm of Robbins and Monroe. I have the references on the stochastic Bayesian inference slide. That combined with the Langevin dynamics, basically. So what is Langevin dynamics? It's basically a way to inject noise, and then the parameter updates, and then the trajectory converges to the full posterior. And the first stage, you do stochastic optimization, then you simulate samples from posterior. With Langevin dynamics, you basically do posterior sampling, which if you were to do it like in the most up-to-date way, I guess would be Thompson sampling is kind of the latest craze right now, if that word is appropriate. So a lot of people use that these days for posterior sampling, but I don't think I've seen any programming implementations yet, but you could do it if you want to. Okay, so the advantage over the Hamiltonian dynamics is basically that you don't need to pull in the whole data set. So especially if these large problems, also kind of comparable to what you've probably seen in the transformer spaces, that most often you need to pull these giant problems into your memory. And that's sometimes not possible anymore. And so having stochastic gradient algebra is advantageous in this sense because it only needs to pull in certain local variables in a sense and doesn't need to pull the whole global context. So that makes the whole thing a lot more memory friendly. And for us, especially if you're compute constrained or if you just, let's say, trying out something on a laptop, for example, or on some slightly larger data, that's obviously a massive advantage. So the point here is that at some point it needs to switch from the stochastic approximation bit to posterior sampling. And that's the key. Hitting the right point to switch between those two dynamics is what makes or breaks this approach. So Robbins Monroe basically suggested these stochastic gradients. They used in stochastic gradient algebra, they used stochastic variation inference, they used in the other more modern inference approaches. And they basically introduced this, add this Gaussian noise, which is then balanced with the step size. As you will see, I think in one or two slides, there also exists very advanced there exist many ideas around what is the right step size or what's the right approach to find the right step size. So basically, stochastic gradient algebra basically boils down to stochastic differential equation. And then if you break it down, this is now the difference expression, but usually it can be viewed as this stochastic differential equation. And then the way they differentiate here between the stochastic approximation part and the posterior sampling, the longitudinal dynamics part is then with the empirical variance. And with that, they compute this alpha. And if alpha is much smaller than 1, then you move to the posterior sampling stage. And I think this is quite recent. So this was, I think, at it was at ICLR 2020. So basically, they had this cyclical step size schedule, and if I'm not completely mistaken, they even scaled it up to a whole city data set on, I think, taxi fares, which is quite large scale or quite high dimensional. So it's really interesting that it worked quite well. Especially if this large data set, it's really nice to not have to pull in the whole global memory. Then here, you basically, in here, they use beta to differentiate here. That's, I'll find then here they have the algebra. So that's comparable. And then performance. So this is now testing on CIFAR 100. So basically on images. Compared to the more classical one, it's a bit better, but you can already see that the stochastic gradient algebra is also quite good. So you can't really go all too wrong here, to be honest. It's a really good algorithm. There's no doubt about it. So moving to variation inference. So this is the other main paradigm. So we have this Monte Carlo pure sampling paradigm, which always suffers from a problem that convergence of 1 over n, and it just takes a lot of samples to converge to the true posterior. But what if you have less computational time, or if you have less, if your workstation is not strong enough, or you have just less computational budget for the inference? Then you can kind of make this inherent trade-off where you say, okay, hey, I sacrifice some of my approximation of the true posterior, and instead I move to this paradigm where I say, okay, I I can approximate the posterior, but I use this proposal, basically a parametric distribution, a distribution family which I optimize over, and I try to get the best approximation I can possibly get. And this is kind of the keystone of this. So you sacrifice your claim to fully approximate the posterior, but within your constrained budget, you try to get the best approach you can possibly get. But again, the pitfall here is that if you have a bad parametric distributional family, then it can't work. Not a chance. So yeah, so you have this family of distributions, which is then optimized. Again, you originally wanted to use Kullback-Leibler, but Kullback-Leibler becomes intractable again, the expectation, which is why you then come to this famous evidence lower bound, as you will see on the next slide. Yeah, so basically this is a tool to approximate densities, whereas MCMC samples from densities, usually underestimates variance. But also it's well suited for large problems and high complexity problems. And also what has come up in the past is, which I think also I mentioned earlier today, is that many people now do this mixture of Monte Carlo and Bayesian inference. Basically, they do a few Monte Carlo runs or a few Monte Carlo samples beforehand, get a much better initialization for the Bayesian inference algorithm, and then they run with it. And that works also quite well. So, I mean, a good initialization is half the game, basically. So we have our family of densities T, and initially you would want to optimize for the KL diversions. Basically, the reach of the density family governs the complexity of the optimization problem. You can decompose the whole thing and you end up with expectations. But Kullback-Leibler is, again, as said before, it becomes intractable for complex distributions. And then we define the third objective, the evidence lower bound. And then the elbow is negative KL diversion plus a constant. So then we basically optimize that. And basically you maximize the elbow is the same as minimizing the KL divergence. So what most of the initial version has been founded upon was the medium variational family, initially coming out of physics. So basically they can capture marginal densities, but that quite well, but they cannot capture the correlation between marginal densities. So that's the weakness there. And people have, of course, as most people do, tried to extend it to what they call like structured problems. Sometimes it works, sometimes it doesn't. It's mostly, again, moving to a paradigm where from a probabilistic programming viewpoint, you're constructing basically a custom designed algorithm, which you try to avoid. So that's the downside there. So this is a very traditional BI algorithm called an ascent. So as long as the elbow does not converge, you always sample Q, and then you compute the elbow. So this is kind of, yes, in a sense, nearly comparable to the Monte Carlo algorithms, but in a sense, you only sample here from the proposal distributional family, D basically. You don't sample from the true model necessarily. Wait, that's wrong. Sorry. You have the true model in P, but yeah. So the predictive So this is really what you're after here, right? So where the HMC with the no-U-turn sample is still in its infancy, you already have a very good average log predictive. So that's really what you want with variation inference. You want to be really quick up here. But then again, here you can kind of see what I alluded to with the Monte Carlo initialization is that you basically here you have different initializations, and they can really make a difference if you have a really good one. So then some clever guys, I suppose, you could say, started thinking about the stochastic approximations as well, like with stochastic gradient reservoir dynamics. Basically, they combined these stochastic optimization with natural gradients, and then they basically constructed stochastic variation inference, which basically subsamples more and more points from the data, analyzes the subsample, implements a closed form update, and then repeats the whole thing. And basically the natural gradient injection or the stochastic noise injection basically alters parameter space in such a way that the KL divergence becomes symmetrized in equal directions. And also natural gradients are much easier to compute than Euclidean gradients, which is quite useful. But again, this was originally, I think, from 2013. If you look at these highly modern frameworks like let's say JAX or Julia a bit, you can basically take gradients of everything. So this problem has kind of like semi-disappeared. Yeah, because you only load in the local values, you can also do extreme scale applications and then basically batch over it. Yeah, and you follow the cheap natural gradients to find a maximum. Step size tries to obey the same condition that's inherent to the stochastic variation inference approach, the stochastic approximation approach. And one of the key ideas here then was that basically you could write the gradients of the elbow of the lower bound as expectation, and then use Monte Carlo samples on that. Basically, again, this is also again the same thing, right? It's a few good Monte Carlo runs as initialization before you run your inference algorithm. Yeah. So this is to basically define a subset schedule. Then you sample data points, compute the local updates, compute intermediate global parameter updates, then you update the global parameter. So this is now one of the examples from original paper, but basically at the time you still had to handwrite the stochastic variation inference algorithm for every single probabilistic models you threw at it, which has disappeared. But at the time, this was still a huge thing. And as you can see, the simple algorithm from earlier really blows up. It's also, it's a hierarchical dirichlet process model. So that's, you have to represent the hierarchies inherently, but it's okay. But yeah, you don't want to write this down every single time. So just to recap, the core idea is you use stochastic optimization to optimize the variation objective, following the noisy essence of natural gradient. You have these adaptive learning rates. There exists some work, I think, from Ranganathan, where basically they define these adaptive stochastic step schedules, which make the whole thing even faster. And given that it doesn't need the global data context, it can scale up to much larger applications. And also what's always inherent to that is there's a lot of work on stochastic optimization. So any advances that happen in there also directly benefit all these stochastic variation inference algorithms. So let's now move to two of the more recent advances in version inference. So basically, this is already like semi-old. So basically, back version inference has this core idea. Again, they use Monte Carlo samples to estimate the gradients of the variational objective, which makes the whole thing a lot more general. It means that you don't have to write this inference algorithm down by hand, but the computer can just do it by himself. So this is why this is one of the first pushes into with version inference into the programming domain. Yeah, so basically you recast the version distribution in terms of a simple function, take expectation, compute the gradients using Monte Carlo, and use these noisy gradients in stochastic optimization algorithms. But then again, here's the problem that you have these gradients. They are unbiased. The estimators follow gradients, but they have a high variance. So you're looking for a way to reduce the variance. So the two ways you can do this is that which they also explored is raw black-ballization or control variance. Yeah. So this is where it rewrites the gradient as an expectation, and then use Monte Carlo to make this expression tractable, basically. Then you can use raw black-ballization to replace certain variables of conditional expectations with respect to a subset of the values, or you can use control variance. As you can see here, using all of them, so using raw black-ballization plus control variance gives the best performance. But it doesn't, but raw black-ballization already improves it a lot. But the basic algorithm, you can see really that the gradients are a bit too noisy. And so you can also see here that there's no real trend which goes down, to be honest. It's, the variance really stays the same. So here we go. So this is the original algorithm, the black version inference, where you still have the sampling here. And then in here, you begin to really use control variance and raw black-ballization to reduce it. And that really improves the variance of the estimator. So if you take the Monte Carlo expectation of some expression, we always talk about it as an estimator afterwards. And inference control variants are a very common technique for that. So this is the I don't think it's the latest shot, but it's one of the it's highly proliferated in probabilistic programming. So basically, problem here, ADVI performs inference in automatic fashion. That's the goal. So you generate the variable algorithm for the defined model. So you can even say it's kind of like a meta inference programmer, if you want to say so. It doesn't really write exact code, but it's kind of assembling the inference algorithm that you want. So what you do here is you do a number of transformations. You transform the latent space such that all the latent variables are in the same space. Then again, you do variational objective as an expectation over Q. With parameterize the gradients, and then use noisy gradients to optimize the variation distribution, which works out of the box quite well. But again, this is really dependent on you having automatic differentiation capabilities, and they need to be efficient. So that's also quite important. Plus, you need to have a defined number of possible transformations for step one of ADVI. So first, you transform the latent variables so they live in the real coordinate space. Then you refine the elbow on the real coordinate space. And then the last trick that you apply is elliptical standardization to make the expectation tractable. In here, you wouldn't get through the integral. You can't really get to the inside and optimize what's in there. But rewriting the integral, the expectation makes it possible, and then you can apply the stochastic optimization techniques and also these noisy gradients. Again, you compute the gradients of the loss with Monte Carlo estimator. And it comes after back-propagation inference, but it performs better than back-propagation inference, even if you apply control variables to back-propagation inference. So that looks quite well, quite good. Same in this case. I think I forgot one statement which I wanted to say in a second. Yeah, what I forgot to say is stochastic gradient algebra dynamics often has problems. Sorry, I'll just quickly jump back. Often has problems with multimodal distributions, which is why they introduced a cyclical step size. So a large step size to move to new modes, and then the smaller ones to really explore those modes. And with that, they really explore these Gaussian mixtures. And yeah. But multimodal is a large problem anyways. So it's not constrained to, let's say, stochastic algebra, but it's a common problem across all inference algorithms. So let's start with Stan. Stan, as if you took, I think, Camille's or something course, it's mostly used by statisticians. It's a very good interface to R. You can express statistical models in there, then perform statistical inference. Has reasonably good libraries with the Hamiltonian Monte Carlo and the neutron sampler, and also ADVI. That defines its own isolated DSL, for which you only have these interfaces for Python, R, and all kinds of other languages. And yeah, it uses reverse automatic differentiation, but core library is in C++, so it's quite an isolated system in that regard. And I mean, the models kind of look a bit like if you would write, let's say, an XML file. So yeah, you have a data block, a parameter block, and then you have to transform parameters and then the model block. Performance-wise, this is from their old paper. So this is obviously looking good compared to what was there before. But there will be a lot more comparisons against newer libraries and newer inference algorithms coming in the next few slides. So yeah, so Venture, which I sent the original paper around. So basically, Venture is especially the paper is really well written. It's quite a long paper, but it's really detailed and it provides a really good insight in probabilistic programming as a, let's say, world. Itself, it's like it's basically a Java virtual machine. Able stochastic control flows, provides a lot of inference algorithms, but also allows for inference programming. There has been intermediate revival, I'd say, with Venture Script, but by now it's not really used anymore. I would be able to link to external models. So, but really interesting thing is that out of the same lab, there came this other framework called Gen, which I will talk to you about in a second. And that was a really massive step forward, and it's really easy to go in there and change parts. Like if you need something to be custom, then you can really just change the code and change the module for yourself. So I'm trying to say this is really modular, sorry. So here's Venture. It's kind of like a bit like a semi-Python syntax. This is for sampling for responsiveness from a Gaussian process, basically again constructing a surrogate. We only want to often expand like a few hundred executions. And then you sample the points from the GP and try to also sample points which could enrich the GP and give it more information. So basically you try to optimize for gain information entropy. This is the typical GP flow, basically, where the more samples you're able to allocate, the better performance becomes around those points. And if you are missing a certain intersections, then of course the possibility is there that it really boosts out, and most often it does. So now coming, I think, to the third framework, it's PyMC3. So this is, again, like a first order probabilistic programming language, very well suited for graphical models, but it's not Turing complete, and yeah, it's not, so it doesn't really satisfy the criteria for a higher order probabilistic programming language. But provides quite a few samplers, has really good documentation. That's something they really figured out. Yeah, it provides first-class support for Gaussian processes. PyMC3, I think, still ran on Theano, but they are working on PyMC4. So let's see, but it's not out yet. So there was a NeurIPS paper, but where they introduced the main ideas behind it, which basically showed that they were using most of the same backend as something which I will show you in a second, but no real performance numbers yet or anything like that. So here, I think this is a classical Python syntax. But what's kind of ugly, to be honest, a bit ugly here, is that you basically have to define your neural network from scratch by yourself, which is not really great because it takes time. You want to be, well, I want to be quick. Yeah, mini batching works well. Really accelerates convergence. Yeah, I think, but most of the modern backends can handle mini batching. So this is now one of the more modern frameworks. Tensorflow Probability, it's also reused. So Tensorflow Probability is reused for PyMC4 as a backend. So it builds on top of TensorFlow, so you have all the normal TensorFlow support. Also the integration with these very big and very deep TensorFlow models. Automatic differentiation support, which mostly happens through XLA, which I'll talk about tomorrow in the afternoon session, basically. Yeah, so but basically XLA is the compiler which drives a lot of this, let's say, machine learning ecosystem these days. So that if you want to port your application through multiple accelerators, then XLA and in essence HLO, which is the intermediate representation for the compiler, is the way to go. The provided inference routines are Hamilton, Monte Carlo, Langevin, no U-turn, version inference. So I guess quite a normal batch here. But the architecture Monte Carlo implementations are really performant because they are fully parallelized on TPUs and GPUs. And that's really something. They're really fast. But again, if you have a model which only runs on a single thread, that doesn't really help. You need, if you have a really performant inference routine, you also need performant model code. So you need to, that's always a balance between the two. So the syntax, I think, is quite normal for the for the eager execution. I think it's eager execution code these days. So that works well. But you can what you can really see here is, which is quite positive, is you can really benefit from the model zoo which is available in TensorFlow. So if you already have experience in TensorFlow, and there are a lot of models out there which are available for TensorFlow, this is it's really nice because you can just import the encoders, decoders, or basically switch other bits of code, which is really helpful. In terms of performance, they all kind of perform the same one here. You can't really tell much, to be honest. So the other big Python competitor in a sense is Pyro, and by now extension NumPyro, which came out of Uber, initially on Torch, but now NumPyro is on JAX, which is kind of like by some viewed as the spiritual successor, like not the successor in terms of production system, but production in terms of research system, where it doesn't constrain as much as TensorFlow does in terms of when you express a model. And basically use, again, JAX with its automation backend to really speed it up. And it can link to bindings, to PPX, for example, if you wanted to. So if you want to, NumPyro is really performant, as you will also see here, for example. They can run on GPUs, they can run on CPUs, they can scale it quite a bit. And especially compared to something like Stan, it's a completely different league. So in terms of syntax, syntax is normal PyTorch syntax, just with a few specific bits here and there. So you have the sample statement, you have to basically register the model. Yeah, you have to define parameters, but that's all kind of normal. Then you have the inference library, which you basically call the pirate infer something. So this is all kind of normal, I would say. So this is using JAX basically, but JAX is more of a functional framework. So you basically define your function up front, and then you basically execute the whole thing in one go, and it's all vectorized, and this stuff runs really fast. Like, so this basically directly uses this, what I mentioned, the XLA compiler, and then just runs like a machine basically. So the XLA compiler is also was behind the latest push by Google with what's called G-Shard. This is a 600 billion parameter model where they basically used a lot of the abstraction from the compiler to really scale it up to the 600 billion parameters. And they tried 1 trillion, but it didn't work, but probably come sooner or later. So Abo2 is kind of adjacent to probability in a sense where it's a lot more low level. So it's a bit more geared towards research. And really tries to embed this probabilistic programming in a deep learning ecosystem. Directly runs on the accelerator hardware, benefits from stuff like TensorFlow Mesh, for example, where you basically try to use complete supercomputers for TensorFlow. Has its main advantage in uncertainty neural networks. So they put out this this work on, I think I have it somewhere down here, Bayesian layers. It's a really interesting paper, I can only recommend it. But that's something they're really good at. And the main developer of Abo2 is also one of the main guys behind this, a lot of the Bayesian uncertainty quantification in neural networks push. So support there is top notch, and the software is also top notch. So you can't really say much against it. But the inference routines are the same as in TensorFlow Probability, so still the highly efficient ones. What's interesting here is what TensorFlow Probability doesn't have is what I just mentioned with G-Shard. One of the key tools of G-Shard is basically that it can do conditional computation, which they call sharding, inside of the compiler. And it basically means that they have these massive networks, and they only compute the parts that they think are important at a time. And hence they can have these much larger models, but in terms of what they train, it's still kind of the same. And LvDS can already benefit from that. But it has much less abstractions than you would usually expect from other frameworks. That's a massive disclaimer there. And to be honest, what one also has to see is that because Tensorflow Probability is a more public-facing framework, there's obviously a lot more documentation behind it. LvDS is a bit less well documented. But it runs well, especially distributed. So here they use an autoregressive flow on a cluster. So this is now a cluster of 4x4 cores. And it communicates well, and the autoregressive flow runs really well. So the performance is absolutely there, but it's a lot more low level. That's the massive disclaimer here. So performance, yeah, it's really good. And also it scales, which is, it doesn't scale linearly here if you look at that, but it's quite close. So that's, what you can really see here, just to point out, is that if you have Stan or PyMC3, which are made for CPUs basically, and you compare it to these modern GPU frameworks, which are able to leverage the hardware they're running on, then performance is a whole different ballgame. So while this might already give you your maximum a posteriori result, for example, this one will still be running. And so you can basically iterate much more quickly with something like LvDS. But you have to write your code in a lower level abstraction, right? So now to Gen, which is kind of the spiritual successor to Venture. It introduces a lot more further abstractions, which kind of differ from the frameworks which I just showed. Basically, it abstracts everything away as generative functions, which basically generates observed from, and you have a completely expandable inference library, which is especially geared towards computer vision robotics, where they did their first trial runs on. It has both a dynamic, which is very easy to write out, but performance is not completely optimized. But if you write in a static DSL, then you'll have much better performance. And inference routines are kind of like the normal stuff, I would say, like Hamiltonian import sampling, sequential Monte Carlo, black box variation inference. Those are, I think, most libraries. And the good thing here is that because it's in Julia, you can A, link it very well with simulators, and also B, and because it's such an modular and expandable library, you can really use metaprogramming here. You can actually construct models with or systems with this, which are really well able to program code itself. So here's the code block. So if you remember the illustration from the beginning, you see this in the beginning you had this very clear flow. You had a DSL at the bottom, inference library in the middle, black box sampler on top, and then out comes the result in here. It's a bit more separated out, but it gives the user a lot more functionality because you can access this generative function interface, and you have a programmable inference. So if you really want to push conceptually what you can do in a probabilistic programming framework, then Gen is really, I think, one of the best ones right now. The syntax is, in a sense, it's Julia syntax plus the trace macros. So basically you define the, so in here you say, okay, hey, Gen, this is one of my functions, which I want to use as a general function. And here you say, hey, I want these variables to be, these certain variables to be traced and added to my base execution trace. So that's the way you would do it in Gen. You can basically just put over anything. So you can put trace over anything. You will just trace the value over the course of the execution trace and then access it out from the chain. Now looking at performance. So it's not always as good as Stan, for example. But that's also sometimes down to the way you do the benchmarks, because Julia is a just-in-time compiled language. So you would first compile the whole thing, we first get it compiled, and then we'll start to run the compiled executable, which something like Stan doesn't have. So in the first iterations, we'll definitely have an advantage there. Yeah, but I mean, so this is here quite close. This is really good. And here, if you use the static modeling language, it becomes really fast. It requires a bit more care and a bit more finesse to define it in the static modeling language, but it's really worth it. So this is PyProp. This is from Etta Loomis, which I mentioned before, this project where they had this massive, where they had this tau lepton decay, the particles particle simulations, did on this large machine. This was the code for which developed for it. It's specifically made for HPC workflows with PPX, but provided inference routines are quite sparse. You only have MCMC importance sampling and then importance sampling with Inference Compilation because that's what they used. So they only ever implemented that. And they have an Intel optimized backend, which obviously does for good performance. But when starting a new project, I wouldn't recommend to look at that because the nature of machines we use is kind of changing. So it's really, I think, a large question whether it's good to optimize for a single platform in a sense, or a platform transcendent approach like XLA, for example. The syntax, in a sense, I mean, it's kind of can be viewed in line with Pyro. They're kind of similar in terms of syntax. Pyro has more functionality. But I mean, the scaling is really good. That's what they're optimized for. All right, so then I think that's should be the last one, I think. So this is Turing, which we'll also use for the in-depth introduction. It's a high-level probabilistic programming language, which Gen is also low-level, but has extremely solid inference routines. It's seamlessly compatible with all the Julia scientific machine learning stack, including differential equations, flux. There's some new, I think Torch J or something like that. There's a new network library in Julia. But I will have a Bayesian deep learning and Bayesian differential equations example tomorrow in the morning session. So to really show how Turing does that, which is it does well. Has really good inference algorithm. The inference subroutines can be composed. You can combine them, which I will show in a second in the tutorial how you can combine different automatic differentiation backends, for example. And here it's, in the sense, it's the Julia syntax with the model macro again, but they put a lot more emphasis on what's called type stability, that you basically predefine the type of your variables so that you can really improve performance. Something which I will also show in the performance optimization part of the tutorial in a few seconds. And basically, yeah, they have the skip sampler, which you combine like particle methods, HMC. You can just combine it across and does well. Those application performance, again, a lot of those frameworks still compared to Stan. So in here, one can really see, I would say, a mixed bag results. The high-dimensional Gaussian is really not doing well. But then again, here, for example, latent tertiary allocation looks good. The rest, well, not perfect. I think just to wrap it up, so just to wrap up the section, so there are many vectors we need to consider when we decide upon which framework we want to use. So one can represent my problem in a respective DSL, or do I require a full-fledged language like Julia, for example? Do I want metaprogramming, which is quite specific? Sometimes you need it specifically for your project. Sometimes you absolutely won't need it, and that's really, I think that's a concern you would have to think about, because if you want metaprogramming, then you're immediately constrained to Julia or Lisp, and Lisp is not that. Lisp is awesome, but yeah. And also, how scalable do I want to be? Do I want to run stuff in the cloud, for example, or do I need burst capacity if I run a large model, for example? And then you have something that way again you want performance portability, and then again something like XLA is a bit better. Do I want to interface with simulators? In my case, yes. That's where the kind of this course came from in the beginning. But if you don't, you have a much broader choice. Do I want to have inference probability? That's also a big thing. General venture, but again, not writing inference algorithms is hard. Like especially writing in an optimized manner is really hard. So often the standard version supplied with the process programming system are often already heavily optimized. So it doesn't make a lot of sense to really invest a lot of time in writing your own inference routines. And then again, an answer which is really open is how high or low level do I want to program? High level, just talking in terms of Julia, for example, it's high level would be something like Turing versus low level is Gen. But in Python, I guess high versus low level would be high level would be Tensorflow Probability, and the low level equivalent then would be Alpha2. But Alpha2 has great capabilities, so it's not an easy choice. I just saw Roman's question in the Slido. I'm not sure there will be a massive shift to ARM, to be honest. But I don't think it makes a difference. XLA, for example, as the abstraction layer, has done really well. And many people basically abstract through the LLVM intermediate representation. And that has proven quite resilient to architecture changes. So I don't think it shouldn't be too difficult. As long as you control your software stack, especially if you need to compile it, for example, that should be fine. And I think if or when ARM proliferates much further, there will also be much better support for it from the Python or Julia guys or the TensorFlow guys, for example. I mean, TensorFlow, I think, already started with because NVIDIA offers ARM on NVIDIA, or NVIDIA on ARM, something like that. Okay, so let's move to the practical introduction. And I think, yeah, we're good on time, I think. Okay, so I'll now pull up the Jupyter Notebook, and I must apologize partially because I want to finish off the repository which basically requires me to, so you don't have to face the torch of installing your own Julia packages with just the, I'll try to push that later. So you can then just run the repository as is. But let me just switch so we can have a look at the tutorial. Hello. Sorry, I'll quickly have to disconnect and connect back in. I don't seem to be able to switch the screen right now. Give me 1 second, please. Yeah, so basically it's a massive library. It has nearly all the distributions you could think of. Multivariate mixtures, univariate, truncated, you name it, they probably have it. Yeah. So now we just start with a normal demo here. So mostly inference is performed using a sample statement, comparable to what we had earlier today with the, I guess, with the eval statement in the higher order and first order probabilistic programming languages. And the available samplers here are the off-the-cuff available ones are Gibbs sampler, Hamiltonian Monte Carlo with dual averaging, important sampling, no U-turn, particle Gibbs, and sequential Monte Carlo, where the last two are particle algorithms. So Gibbs can always be used to combine them. So with Gibbs, you usually combine like a particle sampler with a Hamiltonian sampler, for example. So if you now run this, should hopefully be reasonably quick. We can probably go through the API. So basically, with a Gibbs sampler, you always provide multiple inference algorithms to it. Which basically the Gibbs sampler combines for you. But you have to watch out for when you integrate particle with HMC, for example, then if the HMC is too good, it can be too quick and that can throw off the particle one. And that's something that I guess you have to do with trial and error in a sense. Hamiltonian Monte Carlo, that's the leapfrog step size. That's how you adjust the core values. And that's the number of leapfrog steps to use. That's needs to be defined. Dual averaging takes a lot more arguments, but then in here you have a guidance in the sense that basically even the release paper back at the time was 65% here, and here with the target leapfrog length and the number of samples to be used for adaptation, you kind of just with that you can just do the normal HMC. I would probably do 0 here because it's automatic, automatically determines the step size then, which is occurs as a minor overhead in the beginning, but can converge much faster. And here, you just need to try. Important sampling doesn't need anything. No U-turn sampler. That's a few arguments, but that's again here 0, and here just try and error most often. Particle Gibbs, especially if you do throw particle Gibbs, so PG, into Gibbs itself, what can really help is if you just have an imbalance between an HMC sampler and PG. Then what already really helps if you just boost the number of PG particles. And then inference becomes a lot more accurate. Sequential Monte Carlo, yeah, no argument itself. So, what do we get here? So we get a summary statistics for 2 parameters, and also quantized statistics. And we can also plot that quite easily. But there will be more plots later on. So. we go. The density looks fairly accurate to me, to be honest. So that would be a null distribution. That's so in terms of modeling syntax, what's quite important here is that the order really matters. So because we define S up here and use it in a normal distribution, it needs to be defined before normal distribution. The other way around, it will throw an error and it will give crazy results. That's really important here. We can just sample quickly. That's also. Yeah. Then also Turing provides an interface to use multiple chains for one, but also use multiple threads. So the way it's governed is it depends on how many threads you previously allocated to Julia itself. So in my case, I think I've allocated 8 threads to Julia right now. So it should run fairly quickly. But sure, it should be hopefully be quite quick. Yeah, that looks fine. Basically, you end up with this chain data frame, which contains the different chains, from which you can then extract values if you want to analyze the individual chains. I won't execute this one. I'm not sure what's happening in here. So I tried the sample one. It's supposed to run on all cores, but it doesn't do anything really. This one is just throwing in the So we can basically also directly sample from models prior. So if you do here, just throw in missing values, we'll try to infer those. So it tries to draw them from the distribution. Giving us directly its best guesses basically back. And we can also sample from posterior. But here, what's really important is the missing variables. So if X is missing, it needs to be defined in a much narrower syntax in a sense than just giving in missing. But doing so already does what we want. We're done. There we have our chain. And then again, even in the same, for the same variable in the same execution trace, you have a mixture between missing and non-missing values, which is quite interesting. Basically, so the key is that basically missing entries will always be across the board, are always just random variables to be sampled, which can be quite nice in terms of inferring statistics from your model or from your distribution. And a really interesting bit here, which I think is always really useful, especially if you want some quick statistics from the model that you've thrown up, So just throwing up a simple model problem here again. So this is basically, you can convert the chains into data structures to then analyze them more closely, or also transform them if you want to. But you basically have to abide by a few rules given sampling versus particle methods. And type stability is a big thing here. So yeah, so we have our model here, and basically we can just query our model, which is really interesting. So we can just say probability that x equals 1.0, y equals 1, given that the model is probability query model, is this one up here, s equals 1 and m equals 1. And it will just give you probability. So when you actually define your model in Turing, for example, or just in Julia and give your Julia model to Turing, you can very easily do all these queries on your model. You can ignore values if you don't care what y is, for example. You can also calculate joint probabilities. With that, it's really quick, and the world is literally your oyster, if you want to say so. The same works for chains as well, but the chain syntax is a bit more difficult. I find this one a lot nicer and a lot quicker in terms of data statistics. We also do mode estimation. For that, we need the optimization package. Find our demo. Then we give our data in and get our model basically compiled. Then we can compute our maximum likelihood estimator and maximum a posteriori estimator. Basically spits out the modes that we're looking for. Yeah, and given that it's the optimization package, we again benefit from really the breadth of the optimization package, which is kind of like a hidden package in there. But basically, you can use all these different optimization algorithms to help you find the estimators you're looking for. And here you can also, there are also specific inputs how you can kind of like hack it a bit, where it does more iterations, or it allows the functional to increase and not only decrease over time. And then on top of that, you always have the stat space package. Sorry, got distracted a bit. So you also have the stat space package, which allows you to do all kinds of normal statistical analysis on your model and on your data. So just importing it and basically saying, okay, I want to possibly have maximum likelihood estimator as an estimate, and you can just generate coefficient tables like that and have Fisher information. And there's all kinds of, we'll just quickly pull it up. There exists all kinds of different analysis options in here, where you can really just completely dissect either your model or either a model, or if you just have a raw data set, for example. You try to fit a model, let's say, as an example. Yeah, so basically you have literally the world of statistical analysis at your fingertip in here. Also, they can do chains again. We have again our chain data frame, which we could theoretically transform to a different data type. Then what's also interesting here is that we can there exist all kinds of diagnostics. So you can analyze your chain and how it converges and what it really does. And that's an MCMC chain. It's again, so Julia splits it up into loads of small packages which really interweave together. So it's quite common that you would find this functionality spread out, but most often those packages are from the same people. Yeah, you can basically summarize parameters for your chain and really dissect it here. Also have different sections, different statistics, get certain values out of your chain. And of course, the convergence diagnostics are always interesting when you do the inference for the first time, for example. Yeah. So moving a bit more to the advanced stuff in here. So you can define custom distributions. So basically, custom distributions basically runs through that you define your custom structure. Then you have to, like if you were to implement, let's say, a layer in PyTorch, for example, you have to provide a certain set of functionality. So you have to provide this random number draw, the log PDF, and you have to, within this bijectors package, it basically provides a ton of possible bijections. You have to get the right bijector to biject from this, from a uniform distribution, for example, for this isolated domain into the full real space. And then, because it's uniform distribution here, you'd also define the minimum and maximum, but that's not necessary. It's not necessary for all distributions. And of course, vectorization is nice, but if you just prototype something and you need a distribution which is not in distributions package, which is already quite rare, I wouldn't vectorize it first. It's you just want to prototype it. It's vectorization can wait. And here we also have the internals. So that basically shows what the model macro really does. So in here you define again the Gaussian demo here. And then this is how you would kind of define it without the model macro. So you have to use much lower level functionality, which is which can be good, but can also be quite painful. In a sense, you just access lower level functions. So basically, Turing refers to itself in most ways in here. But so the model is not really, I don't think the model without the macro is all too important. I think it's really more important that you kind of know about the capability around in the ecosystem and how you can really play around with the automatic differentiation and the visualization to get the kind of outputs that you want, be it statistics, be it full-on workflows. So that's, I think, the most important here. In terms of differentiation, so in Julia, there's been, I think it's generally widely accepted that Zygote right now is kind of like probably the most advanced, basically automated differentiation engine, but it still has issues, especially with loops. For loops are a disaster, and it's not improving so far. But basically, yeah, using Zygote, you kind of define a pullback, which is basically comparable to taking an adjoint, or you basically define an adjoint in there if you want to do it manually. And that's what the other automated differentiation frameworks mostly also do. They usually, in one way or the other, they define an automated differentiation backend, and they automatically define the adjoints for your code execution. And then they use that inside of Turing, for example, to provide gradients. So in here, what you really see is that if you apply a pullback from zygote onto sine, for example, then it will return not only the value at that point, but also the function, the derivative, basically. So you can directly reuse it, and it's already computed in the cache of Julia, and you wouldn't need to compile it again, for example. So that's kind of what it looks like. So if you have the back, which is kind of like the function, with a function, some input x, which is splattered here, and you have you can basically just apply it to the gradient of sine at 0.5. So Turing is quite, in a sense, an oddity here because it provides support for multiple automation backends. So yeah, so Zygote is still in the alpha stage. So if you want to do production stuff, I wouldn't recommend it. Yeah, but so forward diff is currently used. It's quite good. But then again, I think one of them was really good for larger problems. I forgot which one it was. Tracker. So if you use Tracker and you have high-dimensional problems, then Tracker provides the best performance. Whereas forward diff, which is the automatic one, is best on lower dimensional variables. Just let it run. I can really mix the different automatic differentiation backends in a way you want to, especially if you say you have just trying to exploit different ones. Let's say you have a high dimensional subproblem that you're trying to sample and a low dimensional one. You could just switch between forward diff and tracker AD, and you probably get better performance than if you use the same one for both. And yeah, this is currently the main issue still, like loops, which you usually have in your code because you cannot vectorize everything. They just incur very heavy performance penalties, and it's not great. So I was benchmarking this variational inference implementation in using Zygote in a different process, so in Gen, and it was horribly slow, like 10, 15 times slower than the previous reverse mode differentiation. And there's no real documentation so far on how you can optimize it or how you can actually get performance out of it. So it's really more of a dark art so far, and there's no real guideline for it yet. So yeah, so as well, Turing likes it if you don't use loops, but that's true for all of Julia or most programming languages in a sense. So here you just use a multivariate normal to just reformulate those two lines into one condensed line. And the other one is this thing for type stability, which is a general thing for Julia, where you wanted to want the input to have a type and the output to have the same type. But it's also an issue of, let's say you have because what the Julia autodiff basically does is it pre-compiles your function that you provide. And if you don't provide types, let's say, it will look at all the possible types that the function could get and compile all these functions, which takes a lot of time. So if you look for more performance, then you're saying, for example, that you just want the float 64, let's say 2 inputs, both float 64 and output float 64 then as well. That's probably the best, because then would then only compile one version of the code, of the model. So that's then a lot easier. So if you look here, then for example, here we have the case. So this would be without type stability or anything like that. But then here, this is with type stability. So this uses just float 64. And it puts out float 64 and everyone is happy. I mean, it can incur memory penalties if you put everything as float 64 and something would rather be like float 32, for example. But if you but you gain in compilation time, and your every single time you throw stuff in, it will also check that it's float 64. So it provides basically a safety net for you having outliers in your data, which might give it the wrong value or the wrong idea. And then basically it just stops there and gives you an error back and says, hey, X is a real value, but I expect a float 64. That's a bad example, sorry. X is an integer, but I expect an integer, but I get a float, for example. And that would be hard to circumvent. But at the same time, it's good for you, because if you provide that function and you want integers input, you probably have an ulterior motive there. So it catching out the floats is quite useful. And you can basically just have this checked with code one type. Basically checks for type stability, and if you would execute that line individually, then it would just give you an basically report how type stable your function is. And you get the whole thing just with putting the macro in front of your function, and that's the job. Another thing that's really useful for us if, in probabilistic programming, especially if you want to use more expensive functions like simulators actually, then memoization. That basically describes that if you use expensive function evaluations, you basically cache them and reuse them later on. So it's, in a sense, it can be a bit compared to a very crude amortization, I guess, but not really reusing it in a sense, but basically just trying to avoid double computing values for a certain point, or for a certain set of inputs. And for that, basically, so it's really easy. Basically, you have to just say, yeah, that's not defined. Okay, so basically here, you just have to say that for it to memorize the function, same arguments, and it just works basically. Just like that, you gain advantage from that, but you need to watch out for memorization in the context of reverse mode differentiation, because that can sometimes give you wrong results. And at the same time, you can also, just as a timing is perfect, I think. You can basically just define here just a test visualization model, and you can just visualize the whole behavior of the whole samplers. So here we have a function that basically just plots the whole samplers. And now we can just be given as abstract types the sampler and the chain. And here we just go through Gibbs samplers, Hamiltonian Monte Carlo, and just start a few. Yeah, we get our surfaces here. And you can really see here with the U-turn, it all looks fine, but you can already see that the tuning here, the parameter makes quite a bit of a difference. With particle, it's also always dependent on how many particles you have. So yeah, I think that's it from my side for today. Let's have a look if there are any more main questions. Slido. I think that's it. If you have any more questions, if you write in the chat, for example, I will try to answer there. Other than that, I think I will see you tomorrow. Bye.
Thank you, Ludger. Bye.